Hello everyone, I hope everyone is good. So today I'm reviewing one another research paper related to reinforcement learning. So give some time. Please give me some time. I'll share my screen. So this one is human level control through deep reinforcement learning. So what is reinforcement learning is being already understood that it is a learning through actions, state or reactions, right? So QKV is the example where we can think about uh, where we can think about graph theory maybe, or we can think about intersection of graph theory and this thing that we can think about the actions which is replicate by themselves, right? So state action and replication of that. There are three basic elements. So what's the basic element of reinforcement learning? Are agent, environment, and action and reward, right? So I've already discussed in my previous research paper that the rewards can considered through different phases, right? So it already I have derived some mathematical computation in my previous research paper. Now I'm discussing more deeply same topic, that is reinforcement learning. So the theory of reinforcement learning provides a normative account, deep rooted in psychological and neuroscientific perspective on animal behavior, how agent may optimize the control of an environment. To use reinforcement learning successfully in a situation and approaching real world complexity, however, agents are confronted with a difficult task. Okay, so they must derive efficient representation of the environment from high dimensional sensory inputs and use this to generalize past experience to new situations. Remarkably, humans and other animals solve this problem through harmonious combination of reinforcement learning and hierarchical sensory processing systems. The former evidenced by the wealth of neural data revealing notable parallels between the phase signals emitted by the dopamine neurons and different differences in reinforcement learning algorithms, right? So it can be considered about movement of a certain object and thinking about that movement and understanding that movement and thing derive things about that movement. So the basic approach is agent, systems, and output, right? So when we think about basics, it is like agent, environment, and action rewards. So this is in parallel to the situations which we can see this, that it can be neural data, which neural notable parallels between phasic signals emitted by dopamine neurons and temporal differences in reinforcement learning algorithms, right? So we can see that different kind of algorithms are already there and their outputs. Unstable or even diverge when a non-linear function or program such as neural network is used to represent action. This instability has several causes. The correlation present in the sequence of observation, the fact that the small updates to Q may significantly change the velocity and therefore change the data distribution correlation between action value and the target value. Okay, we address the instability with a novel variant of Q learning, which uses two key ideas. First, we use a biological inspired by the first we use that biologically inspired by the mechanism term experience replay that harmonize over the data, thereby removing correlation in the observation sequence and smoothing over changes in data distribution. So while other stable methods exist for training neural network in the reinforcement neural fitted Q iteration, these methods involve the repeated training of network they know on hundreds of iterations. Consequently, these methods, unlike our algorithm, are too inefficient to be successful with a large neural network. We prioritize an approximate value of value functions q as a q, right? So it is like an state, action, and output, right? Q0 using the deep convolutional neural network shown in this. Okay, so in previous research paper, I will already discussed DLI method. So I mean, not a DLI method, but something like that. And DLI, it is DLI, right? Yes, it is like deep learning method, right? So it is like where agent learn optimal behavior through trial and error interactions within environment to maximize cumulative reward. Okay, so it is kind of that the agent environment action state reward signal policy and value functions. Okay, so here there is they talk of value function only. So it is convolutional, fully connected layer and no input, right? And output. It is the same thing that it can be moving to a particular direction, or it can give an indication for something, right? It can give an indication for something. Okay, so here it is the digital architecture explained in the method. The input to the neural network consists of 84 into 84 four images produced by processing map. Okay, followed by three convolutional layers, snacking, blue line, difficult and engaging for human players. We use the same network architecture, have a parameter value to demonstrate that our approach robustly learned successfully. Policy over a variety of game based on solely sensory inputs with varied manual mirror knowledge. Okay, notably, our methods was able to train large neural network with using a reinforcement learning. Okay, so it is there, right? So we compared DQN with best performing methods from the reinforcement learning 49 games with the result were available. In addition to the learning energy, we also reduced scores for the professional human games tester playing under controlled conditions. Okay, led by 100% human and 0% random on Y axis, right? You can see that these are training process. Name this game. This is ping pong, Space Invaders, Beam Rider. You can see that when there is a manual playing or automation, right? So it is like at human level or above or below human level. We can see that 69% below human level in the same in a different kind of games. 62%, 97% time pilot. This is 100%, right? 102 free away. Uh, Tun come 112%. Beam rider 119%. So I'm reading page number 4 of 13. Same thing, there are different actions and reactions, and these they can form different patterns, right? Two-dimensional TSNE embedding of the representation in the last hidden layer assigned by DQN to game states experienced by while playing Space Invaders. Okay, I'm reading page number 5 of 13. So this is like working directly with the raw Atari 2600 frames with which are 210 into 160 pixel images with 128 color palette. 84 into 84 into 4 images produced by the processing map. The first hidden layer conventional 32 filters of 8 into 8 with side 4 with the input image applied with rectifier non-linearity. The second layer, hidden layer, consists 64 filters of 4 into 4 with side 2, again followed by rectifier non-linearity. This is followed by third conventional layer that converts 64 filters of 3 into 3 layer with side 1 followed by the rectifiers. So I'm reading page number 7 of 13. So here it is an algorithm, deep Q learning with experience replay. Initialize replay with memory D to capacity. Initialize action value function Q with random weight Q. Initialize target action value function Q with weight this one. Okay, and then repeat that. So we can select the random action 80 and select uh, and probability of e of that random action, and then otherwise select this argument. Okay, repeat that and select random mini batch of transition this. Store transition in this, right? There are different instances of the same input and same output, right? So we can see that qt means this arbitrary term, and this another arbitrary term, and then at and rt, right? So we can see the output. We can see the output. Sample random mini batch of transition this from d if episode terminate at a step j plus 1. uh, Set I plus 1, set ij is this one, right? Otherwise we can form a gradient descent step on this with respect to the network parameter theta. Okay, when we think about the output mechanism, and we can think about the input output value, so we can create a mini batch random mini batch of transition this, and perform a gradient descent steps on this with respect to the network parameter q. Every c step says reset q equal to q. Page number 8 of 13. So visualization of learned value function on two games, breakout and pong. Okay, so visualization of learned action value function on the game big pong, moving toward the pedal controlled by agent on the right side of the screen, and the values of all action around that. So mini batch size, replay memory size, agent SST length, and network target network update frequency 10,000, right? So discount vector gamma used in the Q learning update, this one. So we can see the learning rate. So I'm reading page number 11 or 13. Comparison of games scored by obtained DQ and Egypt with the methods from the literature and a professional human game tester. This one, right? So we can see that random play. We can find the instance and create an instance and finding the optimum value. So the random play output is this: 227.8. Best linear learner is this. Contingency is this. Human is this. DQN normalized DQN 42.7%. So same it apply to different rate. Tennis it is same. 143.2%. In page number 13 of 13, see comparison of DQ and performance with the linear function of approximator, breakout, intro, river, pit, sequence, space invaders. DQN is this, linear is this. Okay. So the reading is this: the performance of DQN agent is compared with the performance of linear function approximator on the 5 validation games with a replay and separate target network. Okay, so this is a 50 million frames, and the output is this: breakout, intro, river pit, seafest, trees and windows. TQN is this, and linear optimal value is this, where the function approximator is linear only. Comparison of DQN with the linear function approximator, we can see the differences, right, of both of them. So thank you so much, everyone. I mean, this is a short review of human level control through deep reinforcement learning. Okay, so I will create more videos on that how we can think about deep reinforcement learning and human control. Thank you so much, everyone.